For the first time in 4 decades, physicists have found a new approach to solving a problem which is almost a century old: how to combine quantum physics with gravity. I told you about this new approach called post-quantum gravity from Jonathan Oppenheim briefly before Christmas. He and his collaborators are now saying that their idea also explains dark matter and dark energy. Let's have a look. This video comes with a quiz that lets you check how much you remember. Quantum physics and gravity don't get along with each other very well. Quantum physics is what we call a non-deterministic theory. It has a random element, it has built-in uncertainty, and it sets limits to what you can know and do. We often say that quantum particles can be in 2 places at once, but really what the math says is that it doesn't make sense to say they're in any particular place. Gravity, on the other hand, is described by Einstein's theory of general relativity. It assigns a time and place to everything. It's deterministic. The future follows from the past, and the only uncertainty it has is that stemming from our own lack of knowledge. There have been many attempts to unify the two and create what's known as a theory of quantum gravity. The best known approaches give quantum properties to gravity and include string theory, loop quantum gravity, and asymptotically safe gravity. The path less taken is to leave gravity a non-quantum theory or to change something about quantum physics. These ideas have not worked out all that well so far. Oppenheim's new idea, post-quantum gravity, now is to combine gravity and quantum physics by giving a random element to gravity. This randomness doesn't come from anything. It's the fundamental ingredient. It's the starting point. This is just like the randomness of quantum mechanics does not come from anything else. It's fundamental, a starting point, just a property of nature. The innovation that Oppenheim brought in now is that he found a way to combine the mathematics of both types of randomness into one framework. In this post-quantum theory, quantum remains non-quantum and particles remain quantum. However, these 2 sectors communicate with each other because particles have gravity, and that gravity in return influences the particles. In Oppenheim's theory, this works without contradictions because these 2 randomnesses fit together. In the new paper now, Oppenheim and his co-author Russo say that this randomness changes the law of gravity under certain circumstances, and those circumstances are when the acceleration of an object is very small. If you follow the debate about dark matter, then this will immediately ring a bell, because the major competitor of dark matter is a modification of Einstein's gravity known as modified Newtonian dynamics, or MOND for short, and that becomes noticeable, wait for it, at small acceleration. The reason this modification at small acceleration can appear as if there was dark matter is that the acceleration on average depends on the strength of gravity. If you're near a planet or sun, like most of you probably are, then you experience a noticeable pull of gravity from those heavy objects. If you interpret that as a force, then that gives rise to an acceleration. The further away you are from heavy objects, the smaller the acceleration. However, the overall gravitational pull coming from the entire galaxy gets smaller the further away you are from the center. This is just because most of the mass of the galaxy sits in the center. It now turns out that if you assume that gravity gets stronger at small acceleration, then that can explain the observations attributed to dark matter in galaxies. This is, in a nutshell, the idea of MOND. Oppenheim now says that when they look at the changes that they get to the law of gravity from this randomness, they see a similar behavior. The smaller the acceleration of an object, the more it's affected by the randomness. They derive an equation that's similar to Newton's law of gravity for the Newtonian potential, and then they have some unusual contributions. They show that these extra contributions seem to be similar to those of modified Newtonian dynamics, which is dark matter's competitor. And for good measure, they also get a term that, they say, looks like dark energy. On Twitter, Oppenheim writes, Folks, something seems to be happening. We show that our theory of gravity can explain the expansion of the universe and galactic rotation without dark matter or dark energy. Okay, but you didn't come to hear what the authors say about their own paper. Let me guess you came to hear what I say. All right, I actually don't like doing this, but here we go. I think it won't work. The reason is that the equation they have is linear in the Newtonian potential. To make modified gravity work, you need an equation that's non-linear in the potential. I haven't had time to think about it much, but I expect that if you look at the scaling of the asymptotic velocity with the mass of the galaxies, it won't come out correctly. The only differential equations that get this right have a rather peculiar non-linear form with a 3/2 exponent. So yeah, I kind of wish it'd work, but I don't think it will. But, you know, I'm just an old grumpy woman who thinks she's seen it all before. So maybe it turns out that what I just said in front of some 100,000 people was complete nonsense. And if that turns out to be so, you don't want to miss my public embarrassment, so stay tuned. Buckle up for some serious quantum stuff. The company D-Wave, which is pursuing a unique approach to quantum computing, has reported a breakthrough. They say they've managed a computation that'd have taken a conventional computer millions of years, which, if true, is the most impressive quantum computation we've seen so far. But is it a computation? Let's have a look. Imagine a bunch of tiny magnets all influencing each other. Physicists call this the Ising model. Riveting stuff, I know, but bear with me. While simple versions of the Ising model can be solved analytically, for difficult couplings between the magnets, their influence on each other can become very complex, including phase transitions in which the collective behavior suddenly changes. Simulating these transitions on a regular computer becomes a nightmare as the system gets larger. And yes, this is the same Ising model that was used by IBM for an attempt to demonstrate that even small noisy quantum computers outperform conventional computers. But as I just told you in a recent episode, another group then did the IBM calculation to better accuracy on a conventional computer. To understand what D-Wave has done, I first need to tell you how D-Wave's approach differs from other quantum computing approaches. D-Wave doesn't attempt to execute logical operations on single qubits. They instead use what's called quantum annealing. Sounds like a hippie retreat, but means you set up a large collection of qubits in a suitable configuration, then you let those qubits relax into an energetically ideal state, which they do on their own, and that ideal state gives you the answer you want to know. D-Wave has been working with thousands of qubits for years, whereas IBM only just reached 1,000 late last year. However, because the two approaches are so different, it makes no sense to just compare the numbers of qubits. Some physicists have argued that D-Wave's machines are not really quantum computers. I'll come back to this later, but first let's look at what they did. The D-Wave team used two of their devices to simulate these phase transitions of the coupled magnet system for a larger collection of magnets than anyone has been able to calculate before. The tricky bit is verifying that it's right, because, you know, no one's been able to do it before. So what they did is that they compared the result of their calculation, that's the blue squares, with the cases of small numbers of magnets where it can be calculated on a conventional computer, that's the line. As you can see, they agree very well. And for a large number of magnets, there are some mathematical approximations from which we know that some quantities of the magnet system obey general scaling laws. Again, their simulation fits remarkably well to the expectation. You can see this in this figure on the right, where the data points are from their simulation and the rectangles are the theoretical predictions. They then estimate how long it'd take to do this calculation on the best current supercomputers. As an example, they use the Frontier supercomputer located at Oak Ridge National Laboratory in Tennessee. It's currently one of the most powerful computers in the world and performs performs more than a billion operations per second. The D-Wave group writes that even for a number of magnets smaller than what they did their calculation for, the hypothetical runtime on the Frontier supercomputer would surpass millions of years. It's actually really impressive. Honestly, I'm much more impressed by this than by the IBM result from last year. Though I have to warn you that this is a preprint and has not yet been peer-reviewed. Now let me come back to the question whether this is a quantum computation. The word computation in general is somewhat vague. You could argue, for example, that any kind of material like this spoon, which I totally coincidentally have here, in some sense calculates the electron bands of a metal. And it's really good at doing this. So in some sense, the spoon is a quantum computer, which would beat any supercomputing cluster. The reason we don't call spoons quantum computers is that they're one-trick spoons. You can't ask them any other question except what a spoon does. Also, as everyone knows, spoons aren't real. We really only speak of quantum computers if you can program the device, and this is where things get complicated. The D-Wave computers can be programmed to some extent, but they're not as universally programmable as the devices that IBM and Google are working on. This is why D-Wave, if you look at the title of the paper, now very carefully says that they're doing quantum simulations rather than calculations on a quantum computer. When they started their quantum simulations, D-Wave was heavily criticized for not making this difference clear. And while I understand why scientists raised this criticism, I always felt it was a little unfair. Because no matter what you call it, they're doing interesting things. Whether you want to call it a calculation or simulation doesn't really matter. I actually think that D-Wave is at this point probably in the best position to make a real impact in commercial applications, though these applications will be more limited than those of universal quantum computers. It's still better than a spoon. Last week, an assembly from the United Nations gathered in Nairobi to discuss climate engineering. They simply failed to come to any conclusions and made no recommendations as to whether we should research it or ban it or just do it. So much about politics, but good thing you have me, because I have no hesitations to offer recommendations. I think climate engineering is a bad idea, but we'll do it anyway because it's the cheapest way to get us out of this unfolding climate disaster. The question is just, how do we do it? This week I have 2 new papers about climate engineering that I want to tell you about. In one, climate scientists have said basically that we better start soon with stratospheric aerosol injections. In the other, they have discussed a new method of climate engineering. Let's have a look. Climate engineering, sometimes called geoengineering, is the deliberate tampering with Earth's climate in the hope of improving human well-being. The most discussed option is stratospheric aerosol injections. That's the idea of spraying tiny particles, that's the aerosols, into a layer of the upper atmosphere called stratosphere. The particles could be brought there by aeroplanes or balloons and would reflect some of the sunlight that we get. If you do it that high up, then the particles won't just drop down but stay there for a couple of years. We know that this does indeed counteract the warming effect from carbon dioxide increase because volcano eruptions sometimes blast ash into the stratosphere, and that does indeed have a cooling effect. Usually the particles that one considers are made of sulfur dioxide. Estimates say it'd take about 10 to 15 million tons per year to counteract the entire warming that we have caused. What makes this idea so appealing is that it's cheap. An estimate from 2020 says that the cost would be as little as $30 billion per year globally. Just in case this isn't exactly your idea of cheap, for context, that's roughly how much Americans spend each year on pet food. The issue is that bringing down the temperature by reducing sunlight does nothing to fix the underlying problem, which is the amount of carbon dioxide in the atmosphere. The carbon dioxide has other consequences, such as ocean acidification, and if the aerosols get washed out of the stratosphere, the warming will very suddenly return, a problem that's been dubbed termination shock. Besides, these particles don't just reflect light that comes from the sun back into space, they also reflect light from Earth back onto Earth. To make matters more complicated, depending on when and where you inject the particles, you'll change wind and precipitation patterns, potentially globally. In the new paper, the scientists now point out there's another problem. Global warming is causing a slowing of ocean currents because their circulation relies on water being cold enough in some areas. I discussed this in detail in an earlier episode. If these currents stop, that'll significantly alter the global distribution of warm water and with that the circulation of warm air. Middle and Northern Europe, for example, would become several degrees colder on average, while Southern Europe would become even warmer. But the effects would be felt globally. It'd also affect a lot of marine animals. That some ocean circulations could stop is one of the climate tipping points that, once we've crossed them, can't be undone, even if temperatures go back down. The authors of the new study now put some numbers behind that. They say that because the ocean temperatures take so long to adjust to air temperatures, if we wait with stratospheric aerosol injections until global warming has reached 4 degrees or so, we'll not undo the damage to the ocean. The message of the paper is clear: we need to start soon. Or as Daniele Visioni, a climate scientist at Cornell University, put it, we can't kick the can down the road forever. The other recent paper that I want to briefly mention discusses a new method of climate engineering, which is to remove water vapor from the stratosphere. Water vapor is a greenhouse gas. We normally don't talk about it because we can't directly influence the water vapor content of the atmosphere. It's determined by thermodynamic equilibrium with the oceans. And there's so much water on our planet that human activity basically makes no difference. However, that's only the case for the lowest layer of the atmosphere, which is very well mixed. These researchers point out that water up in the stratosphere gets there through rather localized channels in certain parts of the world and then stays up there for a long time. If one seeds clouds in these regions with the channels, then that'd decrease the water vapor content in the stratosphere and reduce its warming effects. They call this method intentional stratospheric dehydration. Sounds like a nice idea, but they crunched the numbers and found that the effect would be rather small. It could decrease the entire warming effect by about 1 to 2% of the total we've caused. So good that they looked at it, but not much bang for the buck, and aerosol injections remains the winner. It's a risky idea that can have unintended consequences. Some environmentalists also argue that climate engineering will just give people an excuse to continue pumping out more carbon dioxide and ultimately make things worse. I think, in the end, all this talk about risks and incentives won't matter a bit, because of course the solution that we'll take is the cheapest one. And since we still haven't put a price on carbon, that'll be stratospheric aerosol injections. And that brings me back to this UN meeting, which didn't conclude anything. The obvious thing to conclude is that we need more research on the risks of climate engineering, and we urgently need to come up with a legally binding treaty in which nations agree that if we do stratospheric aerosol injections, we'll still try to reach net zero. Why do these young people have to make it so complicated? All they need to do is watch my channel. Deepfakes aren't on the way, they're here already. Artificial intelligence can now generate images of real people that are indistinguishable from photographs at first, second, and third glance. Videos are not far behind, and I can't wait until I finally look like Keanu Reeves. Several leading news providers, including the BBC, the CBC, and the New York Times, are now about to introduce content credentials to combat the spread of deepfakes. Let's have a look and see if it's the deepfake kryptonite that we've been waiting for. Deepfakes are fake images or videos produced with deep neural networks, which are currently the most powerful type of artificial intelligence. Deepfakes are usually created by swapping one face for someone else's, because creating a face from scratch is God's job. Deepfakes are a big problem because democratic governments rely on people to be well informed, and that's hard if your political leaders can be seen doing and saying anything. Though it'd be fun to see Biden dance with Trump, it'd also be kind of confusing, wouldn't it? This is why many countries and organizations have put money into finding solutions to the deepfake problem that AI has generated. One way you can fight against deepfakes is to try and develop software to tell it apart from the real thing. But this creates an arms race dynamic, or what biologists call co-evolution. The software that allows identifying deepfakes will ultimately just lead to better deepfakes, making them more and more sophisticated. Next thing you know, we're all being ruled by deepfake overlord Bezos, and it tells you a lot about the state of the world that this might not even be an entirely bad thing. The alternative is to better track the origin of images and video footage. The idea is now taking shape with what's been dubbed content credentials, a name so boring you just know it was created by committee. The introduction of content credentials is an initiative by the non-profit Coalition for Content Provenance and Authenticity. It's not one of those well-intended plans that never come into being. It's well on the way already. Many major companies that offer image editing software are integrating content credentials as we speak, including Adobe, Microsoft, and Leica. Alright, but what are content credentials and how are they supposed to work? The idea is fairly simple. You know how any image can store data about what camera settings it was taken with and where it was taken? This is the metadata of the image, and you can find it if you click on Properties of the image file. Content credentials basically add more information to that metadata. This info is encrypted, so it's not that easy to fake. The credentials include who made the image and when and how it's been edited. So if you fired up Photoshop's new AI Frankenstein tool, it'd get locked in the image credentials. The plan is that everyone should be able to check the content credentials on their browser. You just click on the CR icon on the image and it'll bring up the information. One click and you'll know if that viral image of a dog riding on a shark into a tornado was AI generated or, just a normal day in Florida. And that's great, but just exactly how will it prevent deepfakes? It won't. Putting credentials on images doesn't prevent anyone from producing deepfakes. If there's some software in which those credentials are updated automatically, this will make the faker's life a little bit harder, but all they have to do is take a snapshot of the final image and claim it as their own and original work. Now, the Content Credentials website offers a reverse image search where you should be able to search for meshes of one image with other images, and that'll work to some extent. But it has an obvious problem. Photos of one and the same person all kind of look alike, deepfaked or not. And in the end, the problem then comes back to how do you tell apart a deepfake from a genuinely new photo? But content credentials can work nevertheless. It's not because of the image tracking per se, it's to do with the trustworthiness of the image source. If you have an image with credentials from the BBC, maybe, just maybe, you trust it more than something uploaded by Specs Ops Anarchist 4206, who has 7 followers on Twitter. Of course, at the moment, the websites where images are hosted also give us some information, but with the content credentials, it's more directly linked to the content, which I think is a good idea. However, this just brings up the question of who watches the Watchmen. Which sources are we to regard as trustworthy and why? And how are we supposed to check trustworthiness? With trustworthiness credentials? It'll be credentials all the way down. When we discuss the entire deepfake issue, I think we should keep in mind what scientists have found out about why fake news spread in the first place. It's not so much that people are too stupid to identify fake news if they think about it, it's that they don't think about it in the first place. And what good are credentials if no one checks them? None of this is to say that I think it's a bad idea. Every quantum of friction we can add to the deepfake epidemic is worth it. It's just that I think the impact on how we consume and share news will be limited until the day when we'll all be on Neuralink and can just run critical think in store.exe. Won't be long now, I'm sure. Deepfakes. 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 Big data was yesterday's hype, or so you might think. But today's hype, artificial intelligence, is built on big data's foundation. And we're just scratching the surface of AI's potential because of one major obstacle: privacy concerns. Think about getting an AI to analyze your health data to detect issues early. It could save your life, but you'd have to hand over extremely personal information. Here's the amazing thing. New encryption technology makes it possible to get the benefits of data analysis without that privacy trade-off. It allows computation on your fully encrypted data and returns an encrypted result that only you can read. Let's have a look. The technology in case is called fully homomorphic encryption. No, wait, don't go. I know it sounds somewhat off-putting, but the idea isn't all that hard to understand. Homomorphic has nothing to do with Homo sapiens. It's about homomorphisms that are mathematical operations which preserve the relations of the structures they're acting on. A simple example of a homomorphism is multiplication with a constant, say 7, on the real numbers. It's a homomorphism because it preserves addition. You can either take two numbers, add them, and then use the multiplication with 7, or multiply each number with 7 and then add them. Same thing. So this map multiplication by 7 is a homomorphism from the real numbers onto itself. For the homomorphic encryption, the idea is similar. What you want is an encryption that works so that mathematical operations like addition and multiplication can still be done on the encrypted data. Say D is your data, you encrypt your data to E of D, then send this encrypted data to someone else. That other party does the calculation which you asked for. They get a result, send the result back to you, and you unencrypt it. If the homomorphism works as desired, that should give you the same result as if you'd done the calculation yourself on the unencrypted data. The idea of homomorphic encryption has been around since the 1970s, but it wasn't until 2009 that Craig Gentry, an American computer scientist, proved that it's actually possible and also came up with an encryption scheme. You know, I think fully homomorphic encryption isn't the most catchy name ever. If he'd called it the Gentry method, I'm sure by now the birds would be chirping it down from the trees. So it's a fairly recent development. To be fair, the reason it hasn't been widely used so far is probably not the name, though that's quite a mouthful. It's that while it works, doing a calculation on the encrypted data is computationally extremely expensive. The methods that have so far been proposed use an approach called lattice cryptography. But this type of encryption produces a lot of very long strings, and the CPUs and GPUs that your standard computer runs on are not well suited to working with them. So it's slow and it takes up a lot of energy. And let me be clear that when I say the bit strings are long, I don't mean they're 65 bits instead of 64. They can be tens of thousands of bits long. Indeed, the encryption scheme is so complex it's known to be safe from cracking even with quantum computers. This is why there have in the past years been a bunch of companies working on developing computer chips especially for this purpose. This includes Intel, which is working together with DARPA and the Korean Electronics and Telecommunications Research Institute, but also startups like Chain Reaction and Fabric Cryptography. Fabric has a chip that they say is ready to go into mass production and will ship in a few months' time. Intel too says their chip is almost ready and the project will be completed later this year. The Israeli company Chain Reaction is also almost ready to go on the market, and the Korean ETRI says it has a chip already. The idea is basically that companies using these chips can be trusted with your data. Take, for example, the somewhat peculiar case of the British National Health Service, which asked no other than Peter Thiel's company Palantir to overhaul its data management. Not everyone has been excited about this idea. If fully homomorphic encryption was used, it would be possible to work on patients' data while that data remains fully encrypted. And fully homomorphic encryption could also greatly benefit scientific research in general, because it would be possible to analyze all kinds of data that's currently out of bounds because of privacy regulations, especially because of the notoriously tight regulations in the European Union. I find this an amazing development because it's such a nice example for the practical use of mathematics. Homomorphisms on algebraic rings doesn't sound like the kind of maths that'd be good for anything much, but here we go. And it's not that this math has been known for centuries. It's an active area of research where the codes are still being developed. Though if science communication on YouTube has taught me one thing, it's that if you want to be cryptic, maths is your best friend. I recently learned that Q-Day is coming, and it might be here as soon as 2025. What's Q-Day? A new conspiracy theory? Something with quokkas? But no, Q-Day is the day when quantum computers will be able to crack the current encryption protocols that we use on the internet. But there'll also be quokkas in this video. Let's have a look. Quantum computers are devices that exploit entanglement between their computational units, the quantum bits or qubits for short. Entanglement is a type of correlation that only exists in the quantum realm. This entanglement correlation can be moved around, and that can be done in many more ways than are possible on a conventional computer. This is why quantum computers can do certain calculations much faster. One of those calculations that quantum computers can speed up is factoring large numbers into primes. Trouble is that the long time it takes to factor large numbers into primes is the base of the currently most common internet encryption algorithm called RSA, after its inventors Rivers, Chalmers and Edelman. This and similar encryption schemes all rely on mathematical problems that are easy to create but difficult to solve. It's very easy to multiply two large prime numbers, but very difficult to find out the factors given their product. You can use the product as a key to encrypt your data, but if you want to decrypt the data, you need to know the prime factors. You can try getting them by just dividing the number by all possible primes and check whether the result is an integer, but that takes very long time on a conventional computer. The current RSA encryption uses primes of 2048 bits, that's somewhat more than 600 digits in the decimal system. Factoring a number that large on a conventional computer takes trillions of years. A large enough quantum computer, however, could do it within seconds. And that has a lot of people getting very nervous. It's not because the internet will become unsafe. We know encryption protocols that are safe from quantum computers, and efforts are currently underway to switch to those quantum-safe encryption protocols. However, that doesn't solve the problem that in the past a lot of secret data has been encrypted with RSA and similar protocols. If these can be broken, everyone in possession of this data will suddenly be able to decipher it. This is why you can bet any intelligence agency on the planet is currently holding encrypted data from everyone else and trying to get their hands on the first quantum computer to have an early start when everyone begins leaking once secret data. It's a real threat, and if it happens, it'll be a political nightmare. That's why Q-Day is a headache. Not because the internet will become unsafe, but because old data can be deciphered. But just how big does a quantum computer have to be to decode RSA? Estimates from computer scientists say it'll take something like 10 million physical qubits. Physical qubits are the real thing that you have in your quantum computer. They should not be confused with logical qubits, which are hypothetical error-free qubits that are often being used in the computer science literature. The current record for physical qubits is held by IBM and is at roughly 1,000. Though, as I discussed in an earlier episode, we don't know the quality of those qubits, so it doesn't really mean much. In any case, we're far, far away from the number of qubits needed to break RSA. And there are other applications that you could do on a quantum computer before that, because they require fewer qubits, such as solving some problems in quantum chemistry. But Q-Day threats heated up a little over a year ago when a Chinese team claimed in a preprint to have dramatically reduced the number of qubits that had been needed to break RSA. They said that if they combine the quantum calculation with a conventional supercomputer, they can break the 2048-bit RSA encryption with merely 372 physical qubits. If that was correct, that'd indeed be a very big deal, because that'd plausibly become possible within the next 5 years or so. The claim was met with much skepticism. Another group set up to test the result but was unable to reproduce it. So let me just say, I was a little surprised that, according to Business Insider, experts say that Q-Day could arrive as soon as 2025. There's no way. And who are experts anyway? It turns out that experts is Thilo Kunz of Quantum Defense. I hope I'm reading this right. Or should it be Defenfive? Defenfive? Well, whatever the pronunciation, it's a startup which is selling protection against the cyber threats of the future, and it's probably not much of a business to sell protection against threats that, by our reasonable estimates, are at least 30 years in the future. But I promised quackers. What does any of this have to do with quackers? I recently learned on Twitter that there's an Australian company by the name Quacker Quantum that's selling a device called the Quacker Puck, and that they market as your personal quantum computer. It's not an actual quantum computer, it's a conventional computer that simulates a quantum computer. This is known as a quantum emulation. Yes, you can calculate what a quantum computer does on a normal computer, because we can just integrate the equations of quantum mechanics. The problem is, of course, that as the number of qubits increases, this quantum emulation is going to become very slow. Back to the Quacker Pucks. That they were being marketed as quantum computers rather than emulators caused a shitstorm in a tea glass, so to speak, by which I mean few people took notice. I still find it interesting because it highlights a trend we've seen for several years now. There's been so much hype around quantum computing as the technology of the future that companies are popping up left and right to prepare us for the supposed future, like the Quantum Defensive or the Quacker Puck. It's not necessarily a bad thing. I mean, personally, I think there are better ways to waste your money. Check out my Patreon. But then again, that's just me. No, I just find it fascinating how many ways there are to make money from other people's lack of scientific literacy. Maybe I should be selling quantum candy. Thanks for watching. See you tomorrow.